Well, a continuation of what we were looking at. We're looking at relative velocity, and now we're going to look at the relative path. Now, I want us to imagine a scenario where the velocity of a moving body is given. Now, if the velocity of the moving body is given, then it is possible to find its path by integrating its velocity. Okay. So if we consider two bodies, right? If you consider two bodies, A and B, moving with velocities VA and VB respectively. From points, they're moving from points with position vectors A and B. We are having two bodies A and B, moving with velocities VA and VB. From points with position vectors A and B, we know that R is equal to the integral of V dt. One may wonder how this one comes about. From the definition of this, velocity, velocity is the rate of change of displacement. Rate of change of displacement, meaning if our displacement is R, we divide R by T. But because we're saying rate of change, it means that it is dr dt. So when you cross multiply, it means that dr is equals to V dt. So having this, when you integrate both sides, when you integrate dr, you get R, which will be equaling to V dt. So that's how we come to say that R is equal to the integral of V dt. So to get the to get R, we integrate V dt, and this one gives us Vt, because when you integrate V with respect to T, you get Vt plus a constant of integration. Now, the path of A is denoted by VA, so rather by RA. So the path of A is RA, meaning that if the path of A is RA and the path of B is RB, okay, so the path of A is RA and the path of B is RB. So it means that the relative path, okay, if the path of A is RA and the path of B is RB, it means that the relative path or the path of A relative to B would be A path of A relative to B. We denote it like this, and this is equal to relative path of A, rather path of A minus path of B. Okay, but from this general equation, R is equal to Vt plus C, it means that if it is RA is the same as VA times T plus a constant of integration. But at T is equal to 0, at T is equals to 0, we shall have our RA as A, the position of A from the origin. So it will be A when there is no time that has elapsed. So by substituting, we can see that A is equals to VAT, but when T is 0, that is 0, the whole of this is 0, then plus C. So when this is 0, that C is A, and therefore RA is equals to VAT, then plus constant, which is A. The same applies to RB. No, RB is going to be equaling to VBT plus the position of B from the origin. So having gotten these formulas, it will mean that ARB, the path of A relative to B, is going to be equal to RA, which is VAT plus A, then minus VBT plus B. Those ones with the T, we can bring them together. So it will be VA T minus VB T. Then plus, of course, this will be A minus B. So this is VA minus VB, then times time T, then plus A minus B. But VA minus VB is the same as the relative velocity of A to B. So it is A V B times T, then plus A minus B. So that is how we get the relative path. Now by having this, or by taking the magnitude of what we get from here, we can get the value of relative path. Let me do a question, but it all begins, the story begins from this. The story all begins from this, where we have the relative, from the definition of velocity in connection to displacement. So let's have some examples done. Then from there we go to condition for the closest approach. Then from there we shall go to collision of bodies and so on. So a question goes, cars A and B are moving with their respective velocities. To I minus j and I plus j. I plus 3j, sorry. If they are position vectors, for I plus j and 2I minus 3j respectively, find the path of A relative to B at any time t. So given this, we need to first summarize what we are having. So you have given us velocities, velocity of A, and velocity of A has been given as 2I minus j, and velocity of B is given as I plus 3j. Position vectors, position vector of A, so I can call it small a, is equal to 4I plus j, while position vector of B is 2I minus 3j. And show these of signs of vectors. So we're being told to find a relative velocity, rather the relative path of A to B. In other words, they need A RB, and you say that A RB is the same as A minus B plus AVB at time t. So this is 4I plus j minus 2i minus 3j, then plus, of course, one can use this in vector form rather in column form. So AVB, to get AVB, of course, here you have velocity of A minus velocity of B. So we shall have velocity of A, which is 2i minus j, then minus velocity of B, which is I plus 3j, then times time t. So this is the same as 4 minus 2i, that is 2i, then 1 minus negative 3, that is plus 4j. So we are having that, then plus, of course, this is 2 minus 1, so we have I negative minus 3, that is minus 4j times t. So one can end it at this point. Alternatively, because they said in time t, so it can keep like this at any time t. Alternatively, one can use the vector form. ARB would be equaling to A minus B, so you can use column form for 1 minus 2 negative 3, then plus 2 negative 1 minus 1 3, then times time t. So this one still can be 2 4. All right, then plus 2 minus 1, that is 1 minus 1 minus 3, that is minus 4, then t. Well, you can go ahead and say it is 2 plus t, 4 minus 40. Still, that is okay. So at any time t, that is what we get. It's just a matter of coming up with the formulas, and then you get to know how they are applied. So from this, allow me take you to this other part, where we are going to be looking at the shortest distance and time taken. Shortest distance and time taken. Now, whenever there are two particles moving simultaneously from points with their respective position vectors and with their specific velocity, there comes a time when they are said to be closest to each other apart from colliding. Okay, so here we shall, different approaches are used. You can use vectorial approach, you can use geometrical approach, you can use differential approach, but I'm going to specifically be covering vectorial approach and differential approach, for they seemingly look, or for they seem to be very easier for someone to get. So for the case of vectorial approach, for this one, if we suppose particles A and B moving simultaneously with different velocities VA and VB, we're having these two moving with those velocities, from points with position vectors OA and OB respectively, their shortest distance, ds, shortest distance, is denoted or is defined as ds is equal to the magnitude of ARB. The magnitude of ARB is the one that refers to the shortest distance, okay, between these two particles. Now, where this ARB is the path or displacement of A relative to B, as we said. So this is the path or displacement of A relative to B. And for this minimum distance to be obtained, okay, obtain this minimum distance, we dot, for minimum distance to be obtained, for minimum distance to be obtained, the dot of AVB times ARB should be equaling to 0. We dot the relative velocity of A to B with the displacement of A to B. Okay, and then the minimum distance. For minimum distance to be obtained, we dot this. Then the minimum distance itself is the magnitude of ARB. What you need to know that dotting will be helping us get time, which we can substitute in ARB. Remember, ARB is obtained at any time t. So by getting that value of t through dotting, we substitute for it, we get the vector of displacement, then we take its magnitude, and we get the shortest distance. Alternatively, meaning this approach is the commonly used. This approach is the commonest, whereby students dot or you dot to get the time, then you substitute in ARB and you get your value. Alternatively, the time taken, if we need time taken, because we've said that this dot gives us time. So if we alternatively need time taken, still the time taken for that minimum distance to be attained is called time for the shortest distance, which can be obtained by AB dot AVB out of AVB squared. Even this is magnitude. So magnitude of AB dot AVB out of AVB squared, where AB dot AVB is equal to the dot product of AB and AVB. The moment a student uses multiplication sign, it makes everything wrong, because there's a difference between dotting and crossing vectors. So we are not supposed to use a multiplication sign, but rather a dot. All right. Now, for that is the vectorial approach that one can employ. We are going to see how easy it is. Really, this is very, very, very amazing. But for the case of the differential approach, if you are to use differential approach to get the shortest time of the closest approach, still students prefer using this. Now, using relative path as earlier seen, the minimum distance is said to be reached when the derivative with respect to time of ARB, which is equal to the ddt of ARB squared is equal to 0. We shall see for minimum, the derivative should be equal to 0. We are going to see how best. Then after getting the time, okay, the minimum distance still will be ds is equals to the magnitude of ARB. So it's all about getting the value of time. So we can get time by dotting AVB and ARB, or by dotting AB and AVB out of the magnitude of AVB squared, or we can find the derivative of the square of ARB. That is how we get time. Then after getting time, we can easily get ds, or the shortest distance. Then another part that I'm going to enclose into this is the part where we are required to get a point where one body is approaching the other as closer as possible. So let me call it the condition for, okay, condition by one body approach the other as close as possible. For one body to approach the other as closer as possible. Now, if we suppose two bodies A and B moving with velocities VA and VB, okay? From positions OA and OB respectively, if A is to approach B as closer as possible, if body A is to approach B as closer as possible, then VA, velocity of A, which is coming closer to B, dot ARB should be equaling to 0. So you need to note the implication of this. If A is approaching B as close as possible, then VA dot ARB is equal to 0. This one enables us to get time taken by A to get closer to B, and still the distance of the closest approach will be equaling to the magnitude of ARB. Now here we dot the velocity of the approaching object with a relative path or the relative displacement of A to B. All right, so that is what we are having. Let's do some questions and then we see how best we can interpret questions and at least examples. So the formulas are going to be guiding us to do our best. I'll be using two approaches, the differential, and I will also be using the vectorial approach. Okay, examples, question number 1. Particles A and B are moving with velocities 2I plus J plus K, and I, you put the vector signs down, plus 2J plus K from points with position vectors I plus J and 2J plus 3K respectively. Find the Roman 1 time taken for shortest distance to be reached in Roman 2. Find that shortest distance between the particles. Very interesting. So let's use the vectorial approach first. I told you can use 3 of them, but you'll choose the easier one. So you're given velocity of A, and the velocity of A is 2, 1, 1. Velocity of B is given as velocity of B is given as 1, 2, 1. So we are also given OA, whereby from points with position vectors. So if this is for A, position vector is the position of a point from the origin So 1, 1, and OB has been given as 2, 3. So being given this, you see, to get time for the shortest distance using vectorial approach, we dot AVB with ARB. So can we first get AVB? AVB, at least get those marks, is the same as VA minus VB, right? Yes. Oh, I'm sorry for that, members. I'm sorry for that. But we are saying that since to get time, we dot AVB and ARB, let me first get AVB. Okay. So here we are going to be having VA, which is 211, 211, minus VB, which is 121, and this is 1, negative 1, 0. Okay. 1, negative 1, 0. Now, after getting AVB, we can get ARB. You know, ARB is the same as A minus B plus AVB at time t. Okay, so our A is OA, which is 1, 1, minus B, our B is 2, 3, plus AVBT. So AVBT, we already have AVB, so 1, negative 1, 0 times time t. So this is going to be equal to 1 minus 2, which is going to be 1, then of course plus t, so we shall have 1 plus t. Then this is 1 minus 3, which is negative 1, then times negative t, which is rather plus negative t, which is minus t. Then this is 1 minus 3, which is negative 2, plus 0, so just negative 3, rather negative 2. Which brings in the notion, which I told you that to get time for shortest distance, we need AVB and ARB, so that when we dot the 2, but you know, AVB dot ARB, it should give you a 0. So when you dot AVB, AVB is 1, negative 1, 0, dot ARB, which is 1 plus t, negative 1 minus t, negative 2. This one should give you a 0. So this one will give me the value of t. So I will have, with dotting, you multiply and you add. So we shall get this times this, plus this times this, plus this times this. Okay, so we shall have 1 into 1 plus t, plus negative 1 into negative 1 minus t, plus 0 into negative 2, and this should give us a 0. So we shall have 1 plus t plus 1 plus t is equal to 0. So this is 2t plus 2, of course, is 0. So 2t is negative 2. So our time is negative 1. However, we need to know that time cannot be negative, and therefore we shall take our time to be equal to 1 unit. Our time is 1 unit. So that is the first part. That is the first part. Second part of the question asks for shortest distance, ds. ds, we say that it is the same as the magnitude of ARB But here we have to first get ARB when we have substituted the time. So ARB is equal to, we substitute time as 1 unit, not negative 1. So we shall have 1 unit. If we substitute the value of t, we shall have 1 plus t. Oh, yeah, here as we conclude, we say time is 1 unit, but we shall be substituting t as negative, all right? Because here we shall, that is why here even we are having minus t, so whatever time. So here in conclusion, we know that it is positive 1 unit, but here in ARB, we just substitute direct. So it will be 1 minus 1, then minus 1, minus negative 1, then minus 2. So this one will give us 0, 0. I think it is going to 1 minus 3. Right? I don't know why I'm stuck with 2 here. Because AVB. Let me see. My ARB, it was 1, 1, 0. Oh, I made some mistake. I guess I made some mistake here on the positions. The position of A was I and J. That is 1, 1, 0. We don't have the K. Then here, J and K. So we have 0, I, 2, then 3. So it is going to be minus 3. Check that. Let's check that, members. So it is negative 3. Let's check that. So DS will be equaling to ARB magnitude, which will be the square root of 0 squared plus 0 squared plus negative 3 squared. So this is going to be square root of 9, which is 3 units. What I had not put in consideration, you need to quite much observe this. The vectors. IJ, but here they give us J and K, meaning here we have not been given K, so the K is 0, and they have not been given I, so the I is 0. Wow. So from here, yeah, that is the approach of vectors. Now, if someone is to use the differential approach, to use the differential approach, I've told you, of course, we have already gotten ARB as 1 plus t, negative 1 minus t, and negative 3. So if one is to use the differential approach, we know that the minimum is obtained when the t of ARB, which is equals to magnitude of ARB squared, is equal to 0 from our differentiation. So it means now first get ARB squared. ARB squared is going to be equal to 1 plus t squared plus negative 1 minus t squared plus negative 3 squared. So when we differentiate this, the t of ARB squared is going to be equal to, sorry, the magnitude is inside this. So it's going to be equal to, we are differentiating, so it will be 2, 1 plus t decrease the power by 1, right? Minus, like normal differentiation, drop the power, differentiate the bracket, write the power, rather write the function and reduce the power by 1. So if you differentiate 1 plus t squared, you first drop the power 2, differentiate the function inside, which is 1, with respect to t. Then rewrite the function 1 plus t, reduce the power by 1. So that is what I've done, 2 into 1 plus t. When you differentiate here, you drop the power 2, differentiate what is inside, that is minus 1, because when you differentiate this, you get 0. When you differentiate negative t, you get negative 1. Then you rewrite the function negative 1 minus t, then squared. Then here, of course, when you differentiate 3, you get 0. So this is equal to 0. So this is the same as 2 plus 2t, then plus 2. Here the power is reduced by 1, so it is like that. So minus 1 minus t should be equaling to 0. So you can simplify this, 2 plus 2t minus 2 excuse me, let's internalize, otherwise you can easily make a mistake here. Here I dropped the power only, so it is plus 2. Then I differentiated, yeah. So we shall have 2 plus 2t, then minus 2, because this is negative 2, then times this. So it will be negative 2 times negative 1, which is positive 2, then negative 2 times negative t, which will be plus 2t. This should be equal to 0. Simplifying it, so you can put time and it will just come out like this. So this is 40 is equals to negative 4, and still our t is going to be negative 1. But because I need the time is 1 unit, then you substitute the value of t you've gotten into ARB. You're going to get the answer. All right. Let me do you another example. Another example. A particle P starts from a point with position vector two j plus 2k with velocity j plus k. A second particle Q starts at the same time from a point whose position vector is negative 11i minus 2j minus 7k with velocity 2i plus j plus 2k. Find 1, time taken when particles are closest together. 2, shortest distance. 3, between particles. Shortest distance between particles. And 3, find also how far each particle has traveled by this time. Yeah, so for this case, you can use different approaches as much as you can. So you can use different approaches as much as you can, right? Because you have everything. You have got, you've got everything. So, you can use the dot of velocities. You can use the dot of AVB and AR, rather PVQ now and PRQ. Whatever you use, you can get the values. Okay, so let's see time taken when particles are closest together. Now, they have given us OP as 2J 2K. They have given us velocity J plus K. They're giving us OQ negative 11I minus 2J minus 7K. Still, they have given us VQ as 2I plus J plus 2K. So the first part wants us to find the time when the particles are closest together. So you can first get P, the velocity of P relative to Q, PVQ. And this is the same as VP minus VQ. So to get VP minus VQ, it is going to be VP. We've started from J, so we don't have I. We have 1 here, minus Q, VQ. We have 2, 1, 2. So when you take the difference, you're going to get your velocity as -2, -1. And this is 1 minus 1, so 0. We have 0 and then -1 here. Okay, that is PVQ. Then we need to also get, we need to also go ahead to get, we need to go ahead and get PRQ. PRQ is the same as OP minus Q, then plus PVQ times time T, right? So this is the same as P, that is, we have 0I, 2, 2. Then we subtract the Q, which is -11, -2, -7. Then plus PVQ times T. PVQ, -2, 0, -1 times time. So it's going to be 0 minus -11. Okay. We have 0 minus -11. So this is 11 minus 2t. Right? This is 11 minus 2t. Then here you'll have 2 minus 2, which is 0. 2 minus -2, sorry, that is 4. Then this is 0t. Then 2 minus -7. 2 minus -7, that is 9. Then minus t. So that is PRQ. But you know that PVQ dot PRQ should be equaling to 0. So this one will give us the time. So PVQ is this, so we shall have -2, 0, -1 dot PRQ, which is 11 minus 2t, 4, 9 minus t should be equaling to 0. So this is -2 into 11 minus 2t plus 0 times that, that is 0. Then plus -1 into 9 minus t, which should be 0. So this is -22 plus 4t minus 9 plus t is equal to 0. So this is 4t plus 2, that is 5t, is equal to -22 plus -9, that is -31. When you bring it this way, it will be 31. Okay, so it means that our t will be equaling to 31 out of 5. So that is the time for shortest, the time when the particles are closest together. We get it like that. This time you can also get it in other ways. You can use differential approach. Okay, so you can get it in different ways. So that is the first way of getting relative velocity, you get relative path, you dot them, you get time. Otherwise, if one does not want to use this formula, I've not yet gone to this part B, because part B is okay, just a matter of substituting t into this. One can write it in decimal points as t is equal to 31/5, 6.2. One can use it as 6.2 units of time or units. Now, let me show you how you can use other methods too. But this one seems to be the easiest. But if someone wants to use other methods, one can use the differential approach, whereby after having gotten PRQ is negative 2t plus 11 for the negative t plus 9. So if we want to use the differential approach, you can get PRQ squared, which will be, you are going to square negative 2t plus 11, then you square a 4, then you square negative t plus 9. So when you look at this, when you're differentiating now, we know that d dt of p RQ squared should be equaling to 0. And therefore, if you differentiate, you'll be having 2 drop 2 first. It will be 2 into differentiate what is inside. It will be negative 2. Then you rewrite the function negative 2t plus 11, reduce the power by 1. So it will be 1. When you differentiate this one, you get 0. So plus drop a 2, differentiate what is inside, you get negative 1. Then rewrite it, negative t plus 9, reduce the power by 1 and equal to 0. So this is negative 4 into negative 2t plus 11, right? Then this is minus 2 into minus t plus 9 should be equal to 0. So this is 8t minus 44 plus 2t minus 18 should be equaling to 0. So this is 10t minus 44 minus 18, that is minus 62. So this side will be 62. When you divide through by 10, still you get t as 6.2. Someone has used differential approach. Alternatively, still, because we had quoted another third approach of dotting, so still one can get time for shortest distance as PVQ dot PQ, even though you say PQ dot PVQ, the same, I found when I've already written this, over PVQ squared. So we shall first get PVQ. Of course, we have PVQ, and our PVQ was equal to PV minus VQ, which was negative 2, 0, negative 1. That was my PVQ. Then I need to get PQ. PQ is the same as OQ minus OP. I was given those position vectors, negative 11, negative 2, negative 7. I subtract OP, which is 0, 2, 2, and I will get negative 11, because the negative 11 minus 0, negative 2 minus 2, negative 4, then minus 9. After getting this, I first get the dot of PVQ and PQ. So PVQ dot PQ is going to be equaling to the dot product. So the dot product is PVQ negative 2, 0, negative 1 dot PQ, that is negative 11, 4, negative 9. So this is negative 2 times negative 11, that is 22, plus 0, then negative 1 times negative 9, that is positive 9. So this one gives you 31. After getting PVQ, so it means that Down I need PVQ squared. So PVQ squared, PVQ squared would be equaling to, I've already gotten PVQ, so I will need to square it. So it is going to be 2 squared, negative 2 squared, plus 0, then plus negative 1 squared, which is going to be 5. Therefore, my TS is going to be the magnitude of this, which will be 31, out of the magnitude of PVQ, which is 5, which is the same as 6.2. So all the 3 approaches, we've seen that they give you the same answer, 6.2, as time. Now, after getting that value, we can easily get DS. Okay, we can easily get DS because we have the DS is the magnitude of PRQ, and we've already gotten PRQ in terms of time. So simply come and tell me that PRQ is the magnitude, DS is the magnitude of PRQ. So DS, the magnitude of PRQ, and we've already gotten PRQ, so substitute for the time. Simply substitute for the time that we have gotten and get the answer. So first get PRQ. PRQ was equal to negative 2t plus 11. Then we have 4, then minus t plus 9. So this is going to be equal to, when we substitute for t as 6.2, for t is equal to 6.2, substitute, it will be negative 2 into 6.2 plus 11, then 4, then we shall have minus 6.2 plus 9. So this is going to give you negative 1.4. This one will keep a 4, then negative 6.2 plus 9 is going to give you negative, positive 2.8. Then after getting those values, you can compute the magnitude of PRQ. So PRQ magnitude would be equaling to DS, which is going to be equal to the square root of those units squared. So it will be negative 1.4 squared plus 4 squared, then plus 2.8 squared. So by computing the square root, you're going to get the units of distance here. Getting 5.079 units of distance. As simple as that. So all the methods, we've seen that they can give you the same value of t, and then you substitute in the other formula. Part 3 is saying how far each particle has traveled by this time. Find how far each particle has traveled by this time. Find how far each particle has traveled by this time. Now, to get how far particle p has traveled, we integrate velocity of p dt. So it is going to be equal to vpt plus constant of integration. I showed you how this one comes about. So at time is equals to 0, the position of p was equal to 2j plus 2k. So when you substitute there as our RP, it means that negative 2j plus 2k positive 2j plus 2k is equal to, time is 0 here, so it is equal to a constant, implying that Rp is equal to Vp, velocity of P, which was j plus k, times the time, then plus 2j plus 2k, the value of constant. So that is it. So, or one can write it as 0, 1, 1 t plus 2, 0, 2, 2, which is the same as 0 up, then this is t plus 2, then this is t still plus 2. Then now at t is equals to 6.2, we can get Rp. So Rp is equal to 0. All right, it is equal to 0. Then 6.2 plus 2, which is 8.2, 8.2. So it means that at that time, Rp or P will be positioned at at 8.2 J plus 8.2 K. As simple as that. The same applies to Q. It means that even for Q, you are going to follow the same idea. Tell me that RQ would be equaling to VQT plus a constant. But at time is equals to 0, we have RQ, the position of Q. The position of Q will be obtained as negative 11 I minus 2j minus 7k, right? Then you put it here, you replace it at C. Then you substitute for t as 6.2, and you get the position of Q still at that time. So still, this is the same approach which can be followed. All right. Let me do you this tricky one. Then I give you one number to do. At time t is equals to 0, the position vectors of two particles P and Q are I plus j plus 3k and 4i plus 5j plus k, respectively. The particles have constant velocity vectors 2i plus j plus 2k and negative 4i plus 3k, respectively. Show that if P is to approach Q, as closer as possible, then t is equals to 6/7, and find their distance apart. Find their distance apart at this instant. Now, this one brings in the point of that section of the condition that I talked about. When one particle is approached the other as close as possible. Now we don't dot A, V, B, or A, R, Q. No. Here the dotting is specific. We dot. If P is to approach Q, then we shall dot VP with the PRQ. Not the relative velocity. I wanted to revisit my introductory part when I was introducing these things. So we have to be too smart here. Solution. Let's see. Of course, we need to get PRQ. In all cases, we need PRQ. So to get PRQ, we need the relative velocity also. So this is VP minus VQ. Velocity of P is 212, and velocity of Q is this was supposed to be 4J, negative 4J. So we have 0. Otherwise, the proof can, if you alter one value, the proof can fail there and then. So it is 0, negative 4, and a 3. When you take the difference, you're going to have 2, 5, 2 minus 3, that is negative 1 here. Then PRQ, it's the same as PR. Okay, it's the same as P minus Q, then plus PVQ at time t. So P minus Q is the positions of P and Q. So we shall have 113 minus the one of Q, which is 451, then plus PVQT, which is 25 negative 1 times time t. So this is 1 minus 4, that is negative 3 plus 2t. This is 1 minus 5, this is negative 4 plus 5t. 3 minus 1, that is 2 minus t. So, since P is approaching Q as closer as possible, we shall dot VP with PRQ, and we equate to 0 the moment one particle is approaching the other as close as possible. We dot the velocity of that very particle approaching the other with a relative path. So it is going to be VP, which is 212 dot -3 plus 2t, -4 plus 5t, 2 minus t, we equate to 0. So when we dot, of course, here you have 2 into -3 plus 2t, then plus 1 into -4, of course, plus 5t. Then you have plus 2 into 2 minus t equaling to 0. So when you look at this, this is -6 plus 40 minus 4 plus 5t, then minus 4 minus 2t is equals to 0. So summarizing this, 9 minus 2, that is 7t, is equaling to -6 minus 4, that is -10, -10 where could the mistake be? -6 minus 10 plus 5t. Then here we have plus 4. This is a plus 4. Positive 4. Then minus 2t. So -6 minus 10 plus 4, that is a 6 this side. So that your t gets to 6 out of 7. Now, for this case, we are not going to use any other alternative. When one particle is approaching the other, you dot that particle's velocity and its relative path. So that is the only approach we are using in that case. Then find the distance with which they are far apart. So, of course, if they need a distance, we've already gotten our PRQ. So we shall just substitute for the value of t. So it is going to be -3 plus 6 over 7 times this, it will be 12 over 7. Then -4 plus 30 over 7. I'm just substituting wherever there is t. Then here, we shall have 2 minus 6 over 7. So it will give you -9 over 7. When you take the difference here, 7, 28, it will be 2 over 7 and 8 out of 7. So you have that. Then you take PRQ magnitude. When you take the magnitude, you'll be squaring each component under the root. So -9 over 7 squared plus 2 over 7 squared plus 8 over 7 squared. So this one will give you 81 over 49 plus 4 over 49 plus 64 over 49 under the square root. And this one here will give you square root of 149 if you add them, 149 out of 49. And the answer would be 1.744 units of distance. As simple as that. That is how life can be easy. So Let me get you two guiding questions. Let me get you two questions. You do them and see yourselves. One, two particles A and B are moving with velocities I plus j and 2I minus 3j from points with position vectors I minus j plus k and 2j minus k respectively, if A is to approach B as close as possible, find the time for it to do so and their distance apart. Then two, to a particle P and Q a particle P moving with a constant velocity with a constant velocity 2I plus 3j plus 8k passes through a point with position vector six I minus 11j plus 4k. At the same instant, Q passes through a point with position vector I minus 2j plus 5k, moving with constant velocity 3I plus 4j minus 7k. Find the 1 position and velocity of Q relative to P at that instant, then B, shortest distance between P and Q in the subsequent motion, So I'm left with collisions and interceptions. Probably in our next capture, that will be covered. Interceptions and collisions. Wish you the best. Thank you for listening.